now, so you can click got it and also use the mouse.
Oh my God.
Oh, I didn't realize it was on the TV. I was like, it's not doing anything.
Hi.
Okay, so good afternoon. So we are shortwave infrared neuromodulation gadget, also known as SWIM. And our team name is the Infrared Effect, also known as TIRE. So we are TIRE SWIM. And with this project or this presentation, we have fancy new logos. So to introduce myself briefly, my name is Cameron Will. I'm the captain, and I've been working on the software and the laser setup. I'm a computer engineering major.
I'm Matt. I'm an electrical engineer, and I've been focusing on the optical phantom brain.
Yeah, and my name is Vibhush, and I basically just been focusing on the software simulation portion, and I am a computer engineer here. So, from our previous presentations and everything we've done before, our problem statement really hasn't changed too much. It's mainly still on the idea of how can we treat mental disorders such as Parkinson's, Alzheimer's, dementia, and how we can kind of delay the onset of these disorders. And so we are trying to see if we can do this in a non-invasive technique.
Yeah, so our sponsors have stayed the same, still Dr. Krishna, Dr. Arako, and Dr. Z. And then our stakeholders are also the same, still inpatients, outpatients, the FDA, and the doctors and research. Looking at our needs and constraints, our needs are also the same with safety, performance, user-friendly, non-invasiveness, and realistic. And then constraints are also the same as well. No living subject testing and a novel approach. Looking at our requirements, the main changes is with refractive index. Since we went from paraffin wax to resin, there's a different range of refractive index that we were looking at. And then also, if we look at the next slide, we finally have our predicted coefficients for each layer of the head that we were aiming for.
So jumping into our experimental setup, we have this block diagram that we presented before. I figured it'd be good to show it in real life. So we have our same experimental setup with the simulation and software not pictured, of course, but the laser setup, the optical phantom, and the photodetector, which is part of the laser setup. And then again, with the laser setup, again, we have this nice block diagram, but this is what it looks like in real life. So we have our temperature controller, our diode controller, our function generator, our photodetector, integrating sphere, the aspheric lens for collimating the light to make a uniform beam, and then our actual fiber coupled laser as well. And so the only part that really hasn't been discussed before this has been the integrating sphere. So this is what we spent the majority of our time this semester doing, the sample reflectance and transmittance testing, because this final design is mostly like a end goal when you have a completely built optical phantom. But before we get there, we have to test, and we have to find each layer of the head before we can have a complete phantom. And so to test each individual sample, you can look at the graphic that I have up here for measuring transmittance and reflectance using an integrating sphere. And then we plug all of the different measurements into the bottom two equations for transmittance and reflectance. Using those numbers, then we plug it into a program called inverse adding doubling, which is a program specifically made for predicting the absorption and scattering coefficients in biological tissue. So I have the input file that this is essentially what it would look like when you're plugging it in. This was our second batch of resin samples that we have here. And then the output results of that same test with the sample number, the measured and fit reflectance and transmittance. So when you plug it in, sometimes it can't get the exact value for the model that it runs. It essentially runs a Monte Carlo simulation. So if you measure 0.5, it might not be able to get exactly 0.5. In this case, we were able to get the fit exactly on top of it. And then the last two columns are really the big focus of the absorption and scattering for each of these samples.
Yeah, so now we're going to look at the optical phantom setup and getting into the main components. The titanium dioxide as a scattering agent, and then the black dye as the absorption agent are the same. And then we decided to change from paraffin wax to resin for the material. And then looking to the build process, this was the same build process we discussed last semester for the paraffin wax. And then if you go to the next slide, you'll look at the resin process. The resin process is very similar. The only difference is since it's already in liquid form, we don't have to use a hot plate to turn in liquid form. And then we used small cups with hand stirrers instead of our electric stir. So looking at the optical phantom challenges, here's some samples that we first made at the beginning of the semester when we didn't know exactly what we were doing. The biggest problems were sinking and settling with the wax molds. So to kind of change that, we tried making bigger molds so then we could cut off the settling, cut off the sunken portion. And then looking at the first picture, that's exactly what we did. But as you can see, there's still some inhomogeneous parts of the picture as well. So from that point on, we started looking into resin. And if you look at the second picture, that's the first mold we made for resin. And we sanded about 0.1 millimeters off of settling and also sanded through to see how homogeneous the mixture was throughout.
This is the resin. Right?
Yes. And then after after the original sanding, we kind of figured out that it was a lot more homogeneous and a lot more easier to deal with than the wax mixtures. So from that,
This is what your ideal.
That's
Yes.
final, yes.
so after that, we started sticking with resin, and then looking from an actual testing standpoint, with the absorption and the scattering dyes, instead of just the absorption dye affecting the absorption, it also affected the scattering and vice versa. So it was a 2 input, 2 output system instead of just, oh, we could put more black dye in to get a higher absorption. It would also affect scattering as well. So that's another challenge.
Again, so I guess the other major portion of our project was definitely the simulation and the software portion. So again, this is the same from before, but we had 2 major stages of this. One was the pre-processing stage, and the other one would be our actual simulation stage. And the pre-processing stage, we just had all our data, and we wanted to use that data to kind of interpolate the scattering and absorption coefficients to the resolution. And then for the Monte Carlo Extreme, it's a software that you can use to basically get the fluence distribution across like both 2D and 3D media.
So jumping into kind of the pre-processing, this is all, I believe, the same as the CDR. There's a few changes here and there, but this is our initial known data. So this is all biological tissue where we have skin, skull, or scalp and skull from 800 roughly nanometers to 2000 nanometers. So that is within our range of 1550. We have those defined coefficients, but the issue is for the gray matter and white matter, we only go up to 1300 nanometer. So we need to find a way to kind of predict out to 1550 reliably. And so what we did is we looked at the overlap between 800 and 1300, measured the vertical offset between the known layers and the unknown layers, and then predicted out. So this is the gray matter estimation, and then the white matter estimation as well. So it gives us more avenues to explore, looking at the actual coefficients. There's a zoomed in picture. So zoomed in, I've got all these pointers to show what the predicted values are. You saw all these in the table previously. And then to kind of validate if that model is reliable, I did a known versus known test of the skin versus the skull, and that resulted in an R squared of 0.498. So it is a moderate model for this, especially because it's not something that is very well researched for its novel approach.
Okay, yeah, and then so the next portion of it would be the simulation. And so we basically took the coefficients that we had estimated before, and we used something called a 5-layer model of the head in general. And so that's basically the scalp, the skull, the gray matter, the white matter, and the cerebral spinal fluid. And so basically using a Monte Carlo Extreme method. So Monte Carlo Extreme, like before, it's just a software where you can run a Monte Carlo simulation on, if you have a source position, then it will run and give you basically a dispersion pattern throughout the head. And so this is a cochlear penetration zone, so about like the ear. And this is running on just 1 million photons, which is like, in this case, in the instance, it's not as accurate because the laser setup was estimated about 78 quadrillion. And so we basically moved over to the Ohio Supercomputer Center to utilize some of their supercomputing resources to get a more accurate, basically simulation of this. And so there were some challenges that we faced along the way with that. Mainly the main challenges came from just switching from a Windows environment to a Linux like command shell-based environment. And then we also had some issues like utilizing some of the GPUs and things like that, and figuring out how much we actually need. And so as you can see, just using a single GPU for like a 78 billion photon simulation, actually failed in the simulation there. And so after everything was all said and done, we basically got the output results from the supercomputer, and it shows 1515 nanometer photon distribution for 78 billion photons here. And basically each level that you see here, that level is corresponding to a power of 10 in terms of the intensity at that location. And also, we were able to kind of do some analysis on this, and basically this is approximately where the striatum would be. And within that area right there, we were able to get like an average fluence of -5, and then that means your average area, which since fluence is joules over millimeter squared, you can get your average energy, which is about 10 to the -4 in that range. And so that actually means that we do have activation in the striatum using this approach, 1550 nanometer source position. And also, we also did a 3D mesh MCX simulation. This is just with 1 million photons here, but it just gives like a better picture of how the dispersion would work, given your 100 millisecond time window, and then your source position, and it just shows the illumination. Cool. And that would conclude our experimental setup and how we basically went along with the experiment. And I'm just going to give it over to Cam to talk more about the project management.
Yeah, so jumping into the project management, nothing has really changed from last semester about how we manage the project. Our task schedule for this semester is as follows. So most of it was spent, like I said, on the sample transmittance and reflectance, which is our completed and inconclusive test, just because we had samples that matched maybe the absorption, but not the scattering, a sample that matched the scattering, but not the absorption. As Matt said, it's kind of a dual input system. So it was completed, but not quite conclusive. So it's a good foundation for further work, I would say. And then we've also provided a timeline for when did we do which portion of the project, essentially starting from the 10 milliwatt photodetector responsivity, validating that our photodetector works, and then moving into sample development, the analog neuron model, which ended up also not being a viable resource for this semester. And then working into the MCX simulation on the supercomputer, 3D MCX simulation, and then the statistical analysis as well. And then cost estimate in terms of the laser setup, we didn't incur any cost this semester, aside from we did acquire new resources, but luckily they didn't cost anything. So we got our integrated sphere and some optical density filters free of charge from Nanotech West.
Yeah, and then looking at the optical phantom setup, the only difference between this semester and last semester is that since we went with resin, we obviously had to buy the resin material. So that was approximately $200 for our cost.
Yeah, and then I would also like to add, like, we did incur some supercomputer charges, just utilizing like HPC resources. And so we acquired a budget about $1,000, but we used so far about $40. So we'll see.
So looking at the remaining tasks, of course, the sample production is one that still needs to be tidied up or finished up. And then moving on from there, a multiple sample testing the scalp, the skull, the cerebrospinal fluid, and the brain matter all together. And then from a simulation standpoint, looking at neuron activation modeling and the simulation sample testing. So does the simulation values match up with what we're getting in real life with our samples as well? So kind of reflecting back on the semester, our accomplishments were, we built the laser and optical phantom setup. We tested over 25 wax and resin samples. I think it's actually around 28 or 29. And then we also developed a prediction method for approaching unknown coefficients for optical biological tissue, using MCX to simulate 810, 980, 1064. I always mention 1064 and 980 for some reason. And 1550 nanometer biological tissue to kind of see what would be the best approach. And that's how we kind of settled on the Cochlear approach. And then we also discovered and used the inverse adding doubling program to predict the estimated coefficients. And then we also presented at both the Denman Undergraduate Research Forum and the Engineering Showcase. And so looking at recommendations moving forward, for me, looking at kind of a project management point of view, I would just say, more people. Dr. Z, you mentioned it at this design showcase. We probably could have used a whole other team to work on this project, like, I don't know, maybe a hardware and a software team working together. So I would say that in terms of moving forward with the foundation that we've laid, just having a more diverse skill set, I think would be beneficial.
And then for me, from an optical phantom brain standpoint, if we want to continue making them ourselves, I would recommend resin. And then from that point, we'd have to make more resin molds. So we could then come up with a good predicting equation, probably like a differential equation, to kind of predict how the different agents affect each scattering and absorption simultaneously. And then other than that, maybe outsourcing to say a different department so they can better create an optical phantom brain and focus on just the laser testing and transmitting testing and whatnot.
Yeah, and then I guess from a software simulation portion, right? I would say one recommendation that I had, like, having the supercomputing resources was nice, but I think it was actually really difficult to even do the 78 quadrillion photon simulation. And so I guess maybe some recommendation would be like more study in that area to figure out like what we can do to make it like the most realistic approach for that 100 megawatt setup.
Then for the final time, we're going to show you what we don't want to happen. So
We don't want it to go out.
So yeah, we can go ahead and open it up for feedback or questions in the comments.
I came in late, I apologize. So I'm just trying to think through some of my questions. We also talked at the design showcase.
And if you'd like to see any of the previous slides, feel free to let us know.
Can you go back to your timeline?
Sure.
That's,
You're recording about.
oh, got it. Okay, so you go through some of these processes. Obviously, getting to your samples, that was a higher, probably project size, right? And then so you got all these different pieces, and I appreciate the fact that you said, okay, let's see if we can really hone in on the hardware, hone in on the software. So in your mind, I'm just curious, what expertises, what functional attributes does the right team consist of?
I would say one person that Dr. Z brought up was, I believe his name is Dr. Skadar or Skarder. He's in the chemical department, and he actually has a whole thesis and lab dedicated to developing biological tissue, or like maybe not exactly biological tissue, but mock biological tissue. And so that would be gel-based. Okay, certainly with that as well, you can see our resin samples, they do not take into account water. So what he would kind of bring to the table, not only the fabrication, but also your skin's not just dry, it has water in it. And especially with water at 1550 nanometer, that is one of our highest absorbers. So having that just on our optical phantom would be amazing. So like a chemical or a material science, I would say, addition to this team would have really brought a lot of value in terms of getting that kind of sample process moving, I would say.
Anything else?
I agree.
I definitely agree with that.
Yeah. The major barrier there was really just kind of thinking about those considerations.
Yeah.
They started 14 days, so we had to move one, so we kind of lessened the manpower, which I think had an impact.
Yeah.
They had to take on more other projects on their own.
Especially being ECE majors, none of us are material science people. And so all of Matt, what Matt had to do was learn to be able to learn, okay, how do I make a wax phantom? What even is paraffin wax, honestly? Like that kind of stuff. So a lot of learning, he had to do a lot of learning.
Yeah, no, I mean, I could appreciate the work.
Right.
And then a lot of this does sit in sort of the electrical engineering, computer science sort of camp, right? But I'm also kind of impressed with, how far you went into thinking about what's going on in the brain, right? What are the normal processes there? What do you think were pieces of information about neuroscience, about biology that you kind of took away from all of this?
Yeah, I would say for me, obviously you guys can speak on what you guys learned and what you guys thought was valuable, but learning about neurons I thought was really interesting. Going into this project, I knew what a neuron was, kind of. In hindsight, no, I didn't. I definitely know now. I have a better understanding, at least. So looking into like how neurons behave, because my background was I've worked in optics and photonics lab, but I've never worked with optical interactions in terms of biological tissue, neurons, brain matter, all of these different things. So looking at how a photon energy can be translated into neuron activation, and even like, I know Beavis looked into this our first semester, looking at if we activate one neuron, that could set up a whole chain of neurons, that kind of thing. In my brain, I always thought, oh, we need to activate every neuron, and that wasn't necessarily the case. So I would say that was a big learning process, or very valuable in terms of the neurological standpoint, of learning how neurons behave.
And I was studying like definitely about like at least neuromorphology in general. Because for those the I put a model in the 5-layer model. It was like of the scalp, whatever you want. In terms of doing that, there is like a specific like mesh generation algorithm that was used to create everything like that. So it's like you have to know about the layers and how they work and how they and also I didn't realize that there were so many air bubbles in our brain. And so that really does affect
Right.
yeah at least the fluency.
Especially because you're trying to go as deep as you can.
Exactly,
Right.
right? Yeah. So like even in the simulation where you get the average, a lot of the times like it seems like perfectly fine, and then all of a sudden there's like an air bubble and it just throws off all the calculations. Like that.
I'd say for me, the relationship between biomedical, the brain stuff, and then electrical engineering. Like, for example, on the timeline, we did look at an analog neuron model. I didn't know anything about neurons to begin with, but the fact that we were able to kind of look into how breadboarding a neuron model actually could help us get results on how the brain works, I thought that was really fascinating.
I'm going to probe one more question here.
Yeah.
Go ahead, we have 25 minutes.
Okay. Just to satisfy something. What do you think about just the discipline and the learning that happens in electrical engineering, right? Or in sort of your courses of study that make it easier or more advantageous when you're trying to approach neuroscience or these concepts?
Well, one thing like a lot of the way the brain works is deals with like memory potential. Things like that. In general, even like a lot of the modeling for like nuance comes from like an electrical engineering. So that definitely does help out. And then another thing is just in general, like at least in the course of study, you're like taught to think a little more like analytically, and so that just helps out in terms of like being able to create a model, this, and that, and be able to plan things out. So if you guys want to add anything.
I agree.
I would say the foundational classes like EC 2020 analog circuits, EC 2060 digital logic, looking at all of those are very useful for understanding the base. So like the analog neuron model is a great example. If I didn't know what a capacitor was, what an inductor was, what they kind of operated as, I wouldn't have been able to look at the analog neuron model and say, oh, that makes sense how it's representing a neuron. Essentially what the model did was it set a base voltage, and when you applied a laser stimulus, it would spike up, representing an activation of a neuron. And so if I didn't know how those base components worked, I think I would have been completely lost, and I would have had to do a whole course of just learning how each component works. Additionally, the electives, I took an elective called EC 3030. Basically, that was very useful in translating between, okay, what does 1550 nanometer even mean? What is the energy of light? What is a wavelength? All of these different terms that get used and thrown around very quickly. That was infinitely useful in this project, learning about how light interacts with, in that class it was semiconductors, but in this it was biological tissue. So it was a good translation too. So.
All right, a couple questions for you. Now that you've done the simulation with the 1550 nanometer, would you recommend other wavelengths if you wanted to reliably hit other parts of the brain, or would you stick with your original design parameter?
Yeah, I would say based especially on the Brain Impact Project, which I know you're familiar with, but it's our predecessor project. Essentially, I would say if you wanted to target maybe a surface level, you would go with a shorter wavelength, higher energy. But if you wanted to go deeper into the brain, I do think 1550 is the way to go, especially because Brain Impact found that shorter wavelengths cause tissue damage and have that inherent risk. 1550 does not show to have that much energy to cause tissue damage, but it shows like in our average statistical analysis, we can see that in that area of the striatum, we do have enough energy to activate at least one neuron.
How about the 1064 versus the 1550 nanometer?
I think 1064 is really good for like whole head illumination. If you wanted to provide maybe a little bit of extra stimulus to the entire brain. But I think a little bit more investigation in terms of actually using it and simulating it would need to be done.
Yeah, I feel really lightheaded. That's it. Next one would be for the analog one. How about simulating could you potentially use that to simulate other types of neuromodulation in conjunction with photobiomodulation, like say TDCS? Is there any way you could think of to potentially use the analog model to do that?
That's really interesting. So in terms of photobiomodulation, we're very, I'll say, lucky because you can take a laser and a photodetector and use the photodetector as a source for something like TDCS or like TMS. Yeah, it would depend on the components. You'd maybe need a controller board that can take that as an input, like a magnetic field can be input to the system. I wouldn't be as familiar with how to do it, but I think it
At least
is something to
a lot
explore.
of DBS simulations, like people stuff, like that, those kind of simulations, they either take some like an input like DBS current or DBS.
All right.
So that was
What was the biggest problem each of you found in your specific areas, and how did you work around it?
I would say for the laser setup, the integrating sphere, learning how to use an integrating sphere was a bit of a curveball, especially with a photodetector that is a femtowatt photodetector. So our laser is 100 milliwatt. So with a femtowatt, it gets very easily overpowered. So using like optical density filters to filter out 99.99% of light, sometimes even still was not enough for this project. So I would say just learning how to use an integrating sphere effectively and for what we needed to be done for.
Yeah, so for me, definitely trying to learn how to use the paraffin wax, the mold process. As you can see, we started off the trapezoid shape because we were thinking, oh, they could just lay it on its side. Then realized, oh, it needs to cover the integrating spheres. So we had to change that as well.
You can see like where
a lot of things I didn't keep in mind, like sinking or settling, just because how long it takes the wax to solidify and whatnot. So going through all those was kind of my biggest challenge. I think we got to a point with resin where I got comfortable using it and how it works. It was more of just we needed more time to make more molds so we could have a good model that could predict what mixtures would give us what outputs for coefficients.
Yeah, and then for me, honestly, like just using the software and creating some simulations and things like that. A lot of it was the terminology. Like I didn't know like the difference between flux and fluence or things like that. And it just came with a lot of just like trial and error, trying to figure out how to get the data to be formatted exactly how you want it, so you can get those numbers. And so at the end, like learning a lot more about MATLAB and for simple classes.
Well, learning to use the integrating sphere made you a much more well-rounded option. But that said, if you're going to recommend a use case with a closed loop device, what might it be?
I think you had a really good idea about this. Using an Apple Watch.
Oh yeah. So yeah, you can get like gyroscopic data from an Apple Watch, and then in the case that you have tremors or something like that, then you can activate the.
That would obviously just be Parkinson's.
Yeah.
In terms of like dementia or a non-visible disorder or illness, I would say maybe an EEG to sense while the laser is providing a stimulus.
Yeah, and then since cochlear does seem to reach where we want it to reach, at least it can reach that halfway mark, and we can mirror on the other side. It could honestly be like an earpiece.
Well, how about cochlear versus temporal window?
Looking at the cochlear versus the temporal window, it was essentially if you move the laser source up here, essentially, yes, you will get better stimulation for things like the motor cortex, but you would kind of lose some of that striatum or maybe even deeper portions of the brain. From our simulations, I think that the cochlear was the best approach in terms of stimulating both, because especially if you look at the difference between 1 million, so we have a level of 10 to the negative 19 and 10 to the negative 21, and we're not even reaching the motor cortex. And then looking at 78 billion, now we're 10,000 times higher and we're reaching the motor cortex. And we're also only seeing
78 billion, a measly 78 billion, as opposed to the 78 quadrillion that we would expect, so 1,000,000 times more photons.
So this might be maybe, not having enough knowledge about brain, but so you're activating a lot of whole other neurons too, right? How does that impact the patient?
So yeah, that would kind of fall under our remaining task of the neuron activation modeling. So essentially looking into if you input a laser stimulus into the ear, what else is going to happen aside from treating a Parkinson's tremor or something like that, especially because in the ear, you're so close to the auditory nerve. So you could do something like cause ringing in the ears or anything like that. So that would be part of kind of that task. So looking at the actual activation, I'd say the auditory nerve is kind of your biggest cause of concern because it's so close to the source.
So like, there are no frequency in there, right? But are there some aspect that can only activate something like around that box? You know what I mean?
The best approach for that would be like a pulsed approach, because essentially, like in our original real life picture, all the way back in the day, we have our function generator, which we didn't end up using too much this semester because we were so focused on a single sample. But the purpose of the function generator is essentially if you give it some sort of frequency or some sort of pulse width, could you activate those initial neurons and then they can't be reactivated again for another 100 milliseconds or depending on what type of neuron they are. But the idea would be activate the ones that are cause for concern once and then kind of use that time frame to get to the deep portion. Yes, exactly. Yeah.
Because I'm assuming that you don't want to like activate everything at the same time.
Well, I mean,
Or I
yeah,
don't know, like that's the part that my knowledge
Right.
isn't.
I don't know at 1550 what, specifically you'd be doing. But I'm also just thinking about, you're talking about neurons, right? And the brain is much more than just neurons, right? That's just one cell type. And so I always think about, things that we do in the brain as pro-inflammatory. Inflammatory cascade in the brain is one of the things that we really worry about, right? Especially the chronic component of it. So let's say you're somebody who's using this device in the Parkinson's case, let's say, right? Well, is that going to be chronically good for this person, even though it might have a short-term effect that's positive, right? And so what are those then, considerations that you have to have? So how do you think you might test for those sort of unintended effects?
Yeah, I would say going with a pulse approach. So seeing, looking at how the concentration of photons in our very pretty graphs changes when you have a pulsed source rather than a continuous source, because this is essentially a continuous source for 100 milliseconds. It's shooting in 1,000,000 photons. And so using a pulse approach, I would say, then you can see, okay, what is the energy or the fluence at each layer of the brain? And you could probably target specific types with an individual that knows much more. I would say the pulse approach would be a good way to approach that.
All right, kind of a follow-up might be, what about thermal damage to the eardrum itself or some of the tissue inside the cochlear approach?
Yep. So I won't jump back and forth to the first photo again to save your guys' eyes, but we do have a temperature controller that keeps the whole laser. I think we kept it at roughly 23C the entire time we were testing. So that would be kind of the approach there.
I have to, that is my question. I want your reflection on. So the paper that you started working on and based on, it turns out that everything was not as expected and what they reported. So for next team, if like I'm assuming you're continuing this, how would they trust the source? Like what would be your suggestion? Like what do they need to look for in that work to be able to say, okay, this is going to be the base of our work because you worked so far and then you're like, these are not correct. Right. Or the same with the electrical model, right? If you end up like, oh, this is not working. And we at some point talked about maybe behavioral model of this very specific case. So what would be your suggestion for the next team to what to look for to pick the right resources?
I think a more in-depth literature review. I think a lot of our issues came from, we found one paper or between 1 and 5 papers that said, okay, use carbon black dye and titanium dioxide. And they were all saying, use these dyes. But we didn't necessarily look into where they were getting that information because I don't think any of them were original findings. They were all saying, oh, based on this paper, we're using this dye and this dye. So I would say a more in-depth literature review of, look at this paper, why are they using these dyes? And what are the considerations that they take into effect? Because we even found ones that were using the dyes with the paraffin wax, and we still got different results. But they could have accounted for those unknowns that we didn't even look into.
Yeah, I mean, also they could have been using a different process or a better mixer or a better hot plate, stuff like that. So taking that stuff into account, I would say the best option would be to almost expect that it won't work first and then prepare a little bit further down, because then maybe we would have used resin earlier, or maybe would have come up with these ideas earlier, kind of get through these problems.
I also think initial testing was very helpful for us. And I think we learned that like a little bit too late, was we kind of just sold ourselves in the wax and bought a bunch of wax. And then we realized the wax doesn't work. So we bought a little bit of resin, tested it. Oh, it looks promising. Okay, let's use the resin. So then we bought a bunch more resin. So I think if we would have done that with the wax, we could have bought 1 pound of wax, or maybe even less, and made a few samples and said, okay, it looks like their findings are accurate.
Has been the theme of today, so this is like a good presentation. Quick prototyping. So we learned to do like perfect research, perfect everything, then start getting our hands dirty.
Right.
But maybe the better idea is like, you have an idea, test it. If it doesn't work, let it go to the next thing.
Yeah.
And so that's why we have rapid prototyping, right? So I'm glad that is coming up, so that shows that needs to be taught. So it's not a common sense or like first thing everyone will do, like, yeah, let's test it. No, everyone will try to learn a lot. And somewhere you might even get distracted from like the goal, right?
I mean, I think that fits with being a student versus being a researcher. You're taught to just consume the knowledge, right? Then apply it. And here you're finding out that knowledge, right? Some of this stuff, as you said, right? Where did we get this information? Should we be testing across a number of things very quickly? I think that's the normal course, right? So
that's how experience forms, right? And then it becomes you gut and
once you figure that out, then it's hard to turn that part.
it is like, so I actually envision that as a portal. When you go across the portal, like you can't forget it. Like you learn that, it's always I think you crossed the portal.
Yeah.
Congratulations. John, do you have other questions? Ask questions.
The answer will always be
If you could do one thing about the project differently, what would each of you do?
Yeah.
Good question. One thing. No, that's tough. The most
take an R&D project.
I think I still would have taken the project because it was very interesting. I don't know.
I guess for me, it would be pretty much what we talked about, the rapid prototyping.
Yeah.
Even if we didn't start testing it, just seeing if we could make the molds. Like, for example, that mold over there, the one in the gray mold is something that could easily have been done first semester, but we waited till we got into the actual prototyping stage to see, oh, here are the problems, here's how we need to fix them. And then maybe also have another option where you could have had resin at the same time and had a little bit of paraffin wax, a little bit of resin, test and go, see which one that worked out better instead of just committing to the paraffin wax.
I'll say, like, since we have a big picture simulation, right? In terms of like rapid prototyping those samples and things like that, I'll say maybe we can have like simulations where we, just take for one sample, like one block, things like that, just to validate like each sample, like small little samples.
Yeah.
That's us. Because this one, like the big samples that we have recorded, it has all 5 layers. So maybe like one sample just for one layer, another layer.
Yeah. Yeah, I would say kind of the same topic, but from a different lens of project management, because I obviously am a little bit different. I'm the captain, I have to manage the project as well. So I would say taking into account, okay, what can we do before this to essentially eliminate it or validate it would be kind of my learning process going forward, kind of entering that portal of, okay, let's not accept this as truth. Let's just try it out first, that kind of thing. I would say from a project management point of view.
All right, well,